Hind everyone, myself Dr. Bandana Sharma from Ajay Kumar Garg Engineering College. My subject is Engineering Physics, code is KS101T, and the topic which I have started, that is wave optics. And as I have mentioned in my last lectures, that in wave optics there are two parts which is mentioned in our syllabus. The first one is interference, which we have already covered, and today I am going to start with the second part of this wave optics, that is diffraction. So first of all, these are the reference books which you can opt for this topic of diffraction. The first one is a textbook of optics by Ajoy Ghatak, then optics by Brijlal and Subramaniam, a textbook of engineering physics by Navneet Gupta, and you can also follow these two books in order to cover the syllabus of AKTU, that is engineering physics by S.K. Gupta and by S.L. Gupta. Now these are the topics under this topic, under this heading of diffraction. The first one is introduction of diffraction, then types of diffraction. After that, resultant of n simple harmonic motion. We will just go through the resultant of n simple harmonic motion. Then Fraunhofer diffraction due to single slit, double slit. Then Fraunhofer diffraction due to n slit, resolving power and Rayleigh criteria of resolution, and finally resolving power of a plane transmission grating. These are the topics which we are going to cover in this part of diffraction. So first of all, I am going to start with the introduction of diffraction of light. So as you have studied in your lower classes, that diffraction, that is the bending of light. So when light is, suppose you have a source of light, from that source of light you will get the light radiations. Suppose there is an obstacle in the path of light. Now you can say there is an obstacle or there is a small slit in the path of light. Then the light, when it will pass through that particular slit, it will bend around the corners. So that bending of light, that is known as diffraction. Or suppose you have an obstacle in the path of light. Suppose light source is present here, and from that light source you are getting the light radiations. Suddenly, if there is an obstacle in the path of light, then light will spread in the geometrical shadow of this particular obstacle. So that spreading of geometrical shadow or that bending of light, that is known as diffraction. So that is also mentioned over here. When light falls on obstacle or small aperture, whose size is comparable with wavelength of light. So that is the main condition. The source which you are using, the wavelength of that particular source, and the dimensions of that obstacle which you are using in order to get that diffraction pattern. The wavelength and the dimension of that particular diffracting element both should be comparable to each other. So when light falls on obstacles or small apertures whose size is comparable with wavelength of light, the light bends around the corners of obstacle and enters in the geometrical shadow. This bending or the spreading of light is known as diffraction, right? So there is a major difference between diffraction of light and interference of light, that in case of interference, you are going to observe the maximas of same intensities. All the maximas, they are of same intensity, all the minimas, they are of same intensity. Whereas in case of diffraction, you are going to get principal maximas with maximum intensity, and then you will get some secondary maximas with lesser intensities and minimas. And in diffraction, that is obtained because of the superimposition of secondary wavefronts. So there is a difference between diffraction of light and interference of light. So now the type of interferences. So there are two type of, sorry, not interference, I am so sorry for that. There are two, I am discussing here the type of diffraction. So two type of diffractions are there. The first one is Fresnel diffraction, and the second type of diffraction is known as Fraunhofer diffraction. Now what is this Fresnel and Fraunhofer diffraction? That can be understood with the help of a simple diagram. Suppose you have a light source here, then you have a diffracting element. This is a diffracting element. It can be a small aperture, it can be a small slit, it can be an obstacle in the path of light, and this is your screen over which you are going to observe the interference pattern. So this is your source, this one is diffracting element, and this one is screen. So in case of Fresnel diffraction, the distance between this source and diffracting element and the distance between diffracting element and screen, this distance is finite. Whereas in Fraunhofer diffraction, which is your second type of diffraction, the distance between the source and diffracting element and the distance between diffracting element and screen is infinite. So these are two different type of diffraction patterns. In Fresnel diffraction, in this class of diffraction, source and screen are placed at finite distance from the aperture. So that I have already mentioned. In case of Fraunhofer diffraction, in this class of diffraction, source and screen are placed at infinite distances from the aperture. Means from this diffracting element, if the source and screen are at finite distance, that will be your Fresnel diffraction. And if they are present at infinite distance, then that will be your Fraunhofer diffraction. That is the difference between these two different type of diffraction patterns. So you can see here that the first one is an example of Fresnel diffraction, whereas the second one is an example of Fraunhofer diffraction. So in this case, source and screen both are at finite distance, whereas in case of Fraunhofer diffraction, the source as well as screen both are at infinite distance. So in case of Fraunhofer diffraction, what we have to do, we have to use convex lenses. There are two convex lenses are used. The first one that is kept over here, and with the help of that lens, we are going to get parallel light rays, and those parallel light rays will illuminate this particular slit. And there is another lens with the greater radius of curvature. This second lens that is placed between slit and screen, and the role of the first one that it will make the light rays coming from infinite as the parallel light rays, and the role of second lens which we are using here, this second lens that will converge the diffracted light rays over the screen. For example, if we are having 10 light rays which are diffracted through a certain angle of diffraction theta, then all those light rays which will diffract through an angle theta, they will converge at a single point. Suppose there are 10 different light rays which are diffracted through an angle of theta dash. So all those light rays which are diffracted through an angle of theta dash, they will converge at a single point. So that is the role of this second lens which we are using between slit and screen. So that is Fresnel diffraction, and the second one is Fraunhofer diffraction. Now we are having this this particular expression for resultant of n simple harmonic motions. So the derivation that is not in our syllabus, just the mathematical result that if there is a certain point and if n simple harmonic motions, they are passing through that particular point, and all those simple harmonic motions, they are having same amplitude, then what is the resultant of those n simple harmonic motions? So we are having n simple harmonic vibrations having equal amplitude A, periods and phases increasing in arithmetic progression. So what is the meaning of this? Suppose you have the first ray and this one is a second ray, and let delta is a phase difference between them, and then the second and third ray, again the phase difference between second and third is delta, between third and fourth is delta, between fourth and fifth is delta. It means that phase difference is changing in arithmetic progression. So the resultant of all these simple n simple harmonic motions, they can be that can be calculated just by constructing a polygon, and then the closing side of that polygon that will give you the resultant of those n simple harmonic motions. So it is like this: you have a ray with amplitude A, another one with same amplitude A, and the phase difference between the successive light rays, that is changing in arithmetic progression, means the phase difference between first and second is delta, between second and third is delta, between third and fourth is delta, between second last and last is delta. Then you will form a polygon, and this closing side of that polygon, that will give you the resultant of all those n simple harmonic motions. So the addition of all these vectors, that is simply calculated using this, but as I have told you that the derivation of this resultant is not in our syllabus, just the resultant, that what is the final result, that we have to study here. So I am directly telling you what will be the final result. So when you are having n simple harmonic motion, each of amplitude A, and if the phase difference changes in arithmetic progression, then the resultant of these n simple harmonic motion, that will be equal to A sine n delta by 2 upon sine delta by 2. That will be the resultant. And you know the meaning of each and every term here. A is the amplitude of each and every component, N is the number of light rays or number of simple harmonic vibrations. Delta, that is a phase difference between successive light rays. So this is the resultant expression for those n simple harmonic motions, which you have to remember. R is A sine n delta by 2 sine delta by 2. So how you are getting that? Just by constructing that polygon and simplifying it, you are getting this. But we have to remember this expression straight away because the derivation is not in your syllabus. Now using this expression of a resultant of n simple harmonic motions, now we are going to study single slit diffraction, double slit diffraction and n slit diffraction. And in today's lecture, I am going to discuss single slit diffraction, or you can say Fraunhofer diffraction due to single slit. So this is our first topic, Fraunhofer diffraction due to single slit. So in this particular case, what you have a single slit, means you have a slit of very small width. There is a source of light which will illuminate this particular slit, and there is a screen over which you are going to observe the diffraction pattern. So how that diffraction pattern will be formed? So in order to understand this, I am going to start from here. A light beam is incident normally from source S on narrow slit AB. So that slit is AB. So let this is your slit AB. So there is a source of light, and from that source of light will incident over the slit AB. Now in this particular slit, in this slit AB, each and if I am saying that the slit AB is divided into n equal parts and n is very large, then every part of this particular slit that will act as a source for secondary wavefronts. Means when light will incident over the slit AB, then the diffraction of light will take place from every part of the slit AB. And if I am saying there are n equal parts, then the diffraction of light will take place from n parts of this particular slit AB. So what you have, a light beam is incident normally from S on narrow slit AB of width E. So the slit width is, or you can say this AB is small e. According to Huygens wave theory, every point of plane wavefront in the plane of slit is a source of secondary wavelength. So as I mentioned, if we are assuming that there are n parts in the slit AB, then every part will act as a source of secondary wavefronts. Means the diffraction of light will take place from every part of slit AB. So which spreads out to the right in all direction. The secondary wavelets traveling at an angle theta with the normal are focused at point P. So that I will explain with the help of diagram. So let me explain with the help of this. So you are having this slit AB. This is your slit AB, and the width of this particular slit that is mentioned in the previous slide, this width is small e. So this is the width of this slit AB. Now when light will incident, you are having a source of light at infinite, then with the help of a convex lens you are getting parallel light rays which will illuminate the slit AB. Now according to Huygens wave theory, every part of the slit, if I am saying n parts are there, then every part will act as a source for secondary wavefront. So when light will incident over different parts of the slit, then diffraction of light will take place and the light will get diffracted at different angles. Now suppose the light rays which are diffracted through an angle of theta, then you can see that this light ray, this ray number 1, that is diffracted through theta, this ray number 2 that is diffracted through theta, this ray number 3 that is diffracted through theta. So all such type of light rays which are diffracted through same angle, they will converge at a same point. So as you can see here that you are having 3 light rays, only 3 are shown over here, but you know if there are n parts, then you can get n light rays of same amplitude, and for all those light rays angle of diffraction is theta. All those light rays with the help of this lens L, they are going to converge at this point P, and when they will converge at this point P, over that point P you can get a principal maxima, you can get a minima, you can get a secondary maxima. That will be decided by the resultant amplitude at P. And if I am saying there are certain light rays which are diffracted through an angle of 0 degree, means those light rays are passing undiffracted. So when light will incident over the slit, there you can have n light rays for which angle of diffraction is 0. So suppose this ray, as you can see here, for this ray, since this is the direction of incidence of light, so if after passing through the slit light is following the same path, it means that light is and that light is passing undiffracted, or you can say for that light ray angle of diffraction is 0. So you are having n equal parts in this slit. So from those n equal parts you can get n number of light rays for which angle of diffraction is 0. And all such type of light rays, as you can see here, all these light rays, they are going to converge at a single point. For this ray, angle of diffraction is 0. For this ray, angle of diffraction is 0. For this ray, angle of diffraction is 0. Only 3 are shown over here, but you know there are n number of light rays which can pass through the slit undiffracted. So all those are going to converge at this point O. So later on you will see that this point O will be the point of principal maxima. Now how it will be the point of principal maxima, that we will see. But for a general angle of diffraction, that is theta, we are having this point P, which can be a point of principal maxima, minima or secondary maxima. So let's see that how we are going to decide that P will be a point of principal maxima, minima or secondary maxima. In order to decide that, we have to find the path difference between those rays which are superimposing and you are getting the resultant at P. So in order to find that path difference or phase difference, which is further going to decide the conditions of maximas and minimas, what we are going to do, we are going to take two light rays which are diffracted from two extreme corners. So this ray, the ray number 1, that is diffracted from the first extreme corner, that is A, and you can see this another ray, ray number 3, that is diffracted from the second extreme corner, and I am taking those light rays for which angle of diffraction is theta. So you can see that if you are drawing a normal from A on this line number 3, then this angle will be theta. So if you want to calculate the path difference, and I am writing this point as K. So the path difference between 1 and 3, that will be equal to BK. So the path difference is BK, and in order to find BK, you are having this triangle, and in this triangle, this BK upon AB, that will be equal to sine theta. So this path difference, which is BK, that will be equal to delta, and that is equal to AB sine theta. And you know that AB, that is a slit bit, and it is taken as E. So what is the path difference between these interfering rays? It is E sine theta. So it is mentioned over here that the path difference is E sine theta. If this is the path difference, what will be the phase difference? You know the relationship between path difference and phase difference. Phase difference will be equal to 2 pi by lambda times path difference. So using the same logic, you are having this phase difference as 2 pi by lambda E sine theta, because the path difference, this phase difference is written as delta 2 pi by lambda E sine theta. So this is your phase difference, and this E sine theta is the path difference. So now using this phase difference or path difference, we will decide that how you will get maxima, minima and principal maxima. So let us consider that breadth of the slit is divided into n equal parts. As I mentioned, that we are assuming that there are n equal parts in that particular slit, and the amplitude of wave from each part is A. So we are taking that amplitude of the light rays which are passing through each part of the slit, let that amplitude is A. The phase difference between any two consecutive waves from these two parts will be, since you know the phase difference between the light rays which are diffracted from two extreme corners, that phase difference is 2 pi by lambda E sine theta. This was the phase difference between the two extreme corners, and you know between those two extreme corners there are n equal parts. So it means if you want to get the phase difference between two successive parts, it will be 1 upon n times the phase difference between those extreme corners. So this will be the phase difference. So now you are having what you have n number of light rays, each of equal amplitude A, and the phase difference between successive light rays, that is equal to delta, which is 1 upon n 2 pi by lambda E sine theta. And you know the resultant of all these n light rays, that will be equal to this. R will be A sine n delta by 2 upon sine delta by 2. This expression you have to remember from the last result, that R, if we are having n simple harmonic motion, if all are of equal amplitude, and if delta is a phase difference, then the resultant is A sine n delta by 2 upon sine delta by 2. Now using the same formula, I am substituting the value of delta here, A sine n delta by 2 upon delta by 2. So this is the value of delta. After substituting, you are getting this R is equal to this. And in this expression, now what we are going to do, we are going to substitute this pi e sin theta upon lambda as alpha. So if you are substituting this as alpha, so what you are going to find here, this is a sin alpha upon sin alpha by, this will be n. This is not 2, this is n. So the formula is a sin alpha upon sin alpha by n. Now this n is very large, and you know, if n is large, then alpha upon n is very small, and for small value of alpha by n, or you can say for small value of theta, sin theta is approximately theta. So since alpha upon n is very small, so for small value of sin alpha upon n, it is approximately equal to alpha by n. So using this logic, this r will be equal to a as it is, sin alpha as it is, and this sin alpha by n, it is replaced with alpha by n. So this n a sin alpha by alpha, and now we are replacing this n a with capital A. So you are getting this resultant is a sin alpha by alpha. It means over this point P, over this particular point, the resultant amplitude of the n light rays of same amplitude A, and for all those light rays the angle of diffraction is theta, their resultant at this point is a sin alpha upon alpha. And you know what is the value of a here, what is your this alpha here, alpha is pi by lambda e sin theta. So now we have reached at this particular result that r is a sin alpha upon alpha. So if this is a resultant amplitude, what will be the intensity? It will be square of the amplitude. So this I will be r square, which is a square sin square alpha upon alpha square. Now these two expressions, that is one for r and one expression for intensity, these two, they are going to decide that when this P will be the point of principal maxima, when it can be a point of minima, when it can be a point of secondary maxima. That is completely decided by this R and I. So now I am going to decide those points. So first we are going to decide the condition for central maxima, or you can say principal maxima. So now I am going to decide the condition of principal maxima with the help of that R and I. So you know what is the value of R? You know R is your a sin alpha by alpha, right? So if you will see this carefully, then according to this, this point P, that can be a point of principal maxima if R is maximum. And you can see that R will be maximum if alpha is minimum. If alpha is 0, only then you can get the maximum resultant at point P. So you can see if alpha is equal to 0, and you know if alpha 0, then this particular factor, that when alpha tends to 0, what will be sin alpha by alpha? From your theory of limits, that from mathematics, you know that when limit alpha tends to 0, you are having, you are having this factor sin alpha by alpha, it will give you 1. So it means when alpha is 0, this particular factor is going to give you 1. So what will be the value of R then? R will be equal to A in that particular case. And if R is equal to A, then you know that I is square of R, means that is equal to A square. So you will get your principal maxima when alpha is equal to 0. And you also know what is the value of alpha? Alpha is basically pi by lambda e sin theta. So for principal maxima, it will be 0. And since you will get only one maxima with maximum intensity, so there will be one angle of diffraction for which you are going to get maximum intensity. So that is according to this, theta is equal to 0. So what is the condition of principal maxima, or what is the condition for central maxima? For central maxima, you are going to get that central maxima when theta is 0, when alpha is 0, and at that point resultant amplitude will be equal to capital A, resultant intensity will be equal to A square. It means according to this picture, over this point O, since the angle of diffraction is 0, so this O will be the point of, this is the point of central maxima, or you can say this is the point of principal maxima, and over this point you are going to get maximum intensity, which will be equal to A square, because at this point angle of diffraction is 0 degree. So this is the condition for principal maxima. Now we are going to decide the condition for minima. So again I am going to refer the same result, that over point P, resultant amplitude is A sin alpha upon alpha. So according to this, R will be minimum if this numerator, that is equal to 0, or if this R is equal to 0, you are getting minimum intensity. And there is one condition under which you can get R 0, and the condition is sin alpha 0, but alpha should not be equal to 0. That is the condition, because if alpha will be 0, then the sin alpha upon alpha, that will be 1, and that is a condition of principal maxima. It means for minima, the condition is that sin alpha should be 0, but this alpha must not be equal to 0. So this is the condition. It means alpha should be equal to plus minus m pi, where m starts from 1. It can take all the integers values 1, 2, 3, 4 and so on, but m is not equal to 0. Again the logic is same. If m will take 0 value, then alpha will be 0, and you know alpha 0 is the condition of principal maxima, that cannot be a point of minima. So this is your condition for minima. So for minima, sin alpha 0 and alpha is not equal to 0. I hope this is clear. And you know, if sin alpha 0, then alpha is plus minus m pi, where m starts from 1 and m is not equal to 0. So you have to remember this, that m is not equal to 0 here. And you know that alpha is pi e sin theta upon lambda. So you are substituting here, alpha is pi e sin theta upon lambda, which is equal to plus minus m pi for minima. This pi will get cancelled, and you are getting this condition, e sin theta is equal to plus minus m lambda. This is the condition of minima in a single slit diffraction pattern. Clear? So you are getting maxima when alpha is 0, when theta is 0. This is the condition of maxima, principal maxima. You are getting minima when alpha is plus minus m pi, but m is not equal to 0. That you have to remember. And in terms of theta, the condition is e sin theta is equal to plus minus m lambda. That is the condition of minima here. Now you have principal maxima, you have minima. Now let's decide the condition of secondary maxima. So in order to find the condition of secondary maxima, what we have to do, you know that I is equal to a square sin square alpha upon alpha square. So as you can see here, that I is depending upon alpha. This intensity, resultant intensity, is depending upon this factor I. And you know, in mathematics, if you want to find the condition of maximas and minimas, then if y is a function of x and you want to find the points of maximas and minimas, then you have to differentiate y with respect to x, and then you have to equate it to 0. And then you can decide your conditions of maximas and minimas. Since I is a function of alpha, so in order to find the conditions of maximas and minimas, you have to differentiate that I with respect to alpha, and then you have to equate it to 0. And after that you can decide that what are your points of maximas and minimas. So in order to do that, what we have to do, we have to differentiate this I with respect to alpha. So you can see here that di upon d alpha. So this a square, that is written as I naught here. So this is equal to a square, and if you will differentiate it, it will be alpha 4 and then alpha square 2 sin alpha cos alpha minus the second part is sin square alpha 2 alpha. So that is the differentiation, and if you will differentiate it, after differentiating you are getting this condition. This one is the condition which you are getting after differentiating. Now you can see in this particular condition that in order to this product to be 0, you are having different conditions. You know this 2 I naught, that is constant, that cannot be 0. Now the next one is this sin alpha can be 0. If sin alpha is 0, then this entire product of this term of left hand side, that will be 0. But you know that sin alpha is equal to 0. That is a condition of your minima. So you cannot take it as a condition of maxima here. So the remaining condition is this sin alpha cos alpha minus sin alpha is equal to 0, or you can say sin alpha is equal to alpha cos alpha, or just give me 1 minute, or you can say alpha is equal to tan alpha. So this alpha is equal to tan, how you are getting it, let me differentiate it, and after differentiating I will explain that. You have I as a square, give me 1 minute, you have I as a square sin square alpha upon alpha square. So if you will differentiate it, this I with respect to alpha, you are going to get here a square as it is, it will be alpha raised to power 4, it will be alpha square 2 sin alpha cos alpha minus sin square alpha 2 alpha is equal to 0. Now you can see what is the common factor here. you can see that 2 alpha is common. So I am taking 2 alpha common, a square is already there, and one more factor, that is sin alpha, is also common, and I am writing that alpha 4 here, and the remaining factor over there is alpha cos alpha minus sin alpha is equal to 0. So you know this entire product, this is equal to 0. So this can be 0 if one of these factors is equal to 0 or all the factors are 0. You know this 2 is not 0, a square is not 0. So now the first condition, that is alpha can be 0. If alpha is 0, then the entire product is 0. But you know alpha 0 is the condition of principal maxima. So that condition is already decided. The second condition is if sin alpha 0, then the entire product will be 0. But you know sin alpha 0 is the condition of minima. So again, that condition is already decided. Now the remaining factor, alpha cos alpha minus sin alpha should be 0. So since these two conditions are already decided, that alpha 0 is principal maxima, sin alpha 0, that is your minima, it means the remaining condition, that alpha cos alpha minus sin alpha 0, or you can say alpha cos alpha equal to sin alpha, or you can say alpha equal to tan alpha. So that remaining condition will be the condition of secondary maxima. So this alpha equal to tan alpha is representing the condition of secondary maxima. Now this alpha is equal to tan alpha, we have to decide the points of intersection of this alpha equal to tan alpha, and these points which are mentioned over here, these points are the points of intersection of alpha is equal to tan alpha. So how that is decided? You can take y is equal to alpha. If I am taking y is equal to alpha, then y is also equal to tan alpha. And you know what, if you will plot a graph between y and alpha, along that direction you have y, along x-axis you have alpha. What will be the graph between y and alpha? That will be a straight line passing through the origin. So this line is representing y is equal to alpha, a straight line passing through the origin inclined at 45 degree. And y is equal to tan alpha, you know that graph will be like this. And now the points of intersection, you can see the first point of intersection is this, but you have to ignore this point because this is a point of principal maxima. So you cannot take it as a point of secondary maxima here. So you have to ignore this point. Then the next point of intersection will be 3 pi by 2. Next will be 5 pi by 2, next will be 7 pi by 2, next will be 9 pi by 2, 11 pi by 2, and similarly on the opposite side, on minus 3 pi by 2, minus 5 pi by 2, minus 7 pi by 2. It means the point of intersections are 3 pi by 2, 5 pi by 2, 7 pi by odd multiple of pi by 2. You have to ignore 0 because 0 is representing your principal maxima. So your first secondary maxima that will be observed when alpha is plus minus 3 pi by 2. If alpha is this, then what will be the intensity? It is simply a square, which is represented as I naught sine square alpha upon alpha square. Instead of alpha you will write 3 pi by 2. So after simplifying you are getting I naught upon 22. For secondary maxima, you know the point is alpha is equal to 5 pi by 2. So you have to substitute the value of alpha as 5 pi by 2. After simplifying, you are getting it is 4 upon 25 pi square of I naught. And then next one is 4 upon, next point will be 7 pi by 2. So that will be 4 upon 49 pi square I naught. So in this way, you can see the intensity of secondary maximas that will go on decreasing. So the ratio of maximas, you have one principal maxima with intensity I naught. Then you have first secondary maxima with intensity 4 upon 9 pi square I naught. Then you have next secondary maxima with intensity 4 upon 25 pi square I naught. Then the next one is with intensity 4 upon 49 pi square I naught. So if I will talk about the relative intensities of maximas, then it is like this. 1 is to 4 by 9 pi square is to 4 upon 25 pi square is to 4 upon 49 pi square and so on. So that is the ratio of maximas. And if you will plot a graph between I and alpha, then graph will be like this. So how you are getting that graph? You know your principal maxima that is obtained when alpha is equal to 0. So this is alpha 0. At this point you are getting a principal maxima, and the principal maxima is of maximum intensity, which is I naught, which is your a square. After your principal maxima, on both the sides you are going to get minimas, and you know the points of minimas. Minima is obtained when alpha is plus minus m pi and m is not 0, m is starting from 1. It means your first minimas, they are obtained at plus minus pi. So these are the position of minimas on both the sides of this principal maxima. After that, you are going to get your first secondary maxima at 3 pi by 2. So this point is 3 pi by 2, this one is also 3 pi by 2, and it will be 4 by 9 pi square of I naught, and it is written, it is simplified and the value of pi is substituted. So it is 1 upon 22 times of a square. Then second secondary maxima, that is obtained at 5 pi by 2, next at 7 pi by 2, next at 9 pi by 2, and so on. It means the intensity of these maximas, that will go on decreasing when the number of maximas will increase. Means a principal maxima that is having maximum intensity, and when you are moving towards your first secondary maxima, then second secondary maxima, then the intensity will go on decreasing. So you are going to get principal maximas, then minimas, then secondary maximas, then minimas, secondary maximas, then minimas, but these maximas, their intensity will go on decreasing. So this is your single slit diffraction pattern, means the maximum intensity in a single slit diffraction pattern, that will be concentrated over the principal maxima. So that is the intensity distribution pattern. So this is all about your single slit diffraction pattern. So you know what are your condition of principal maxima, minima, and secondary maxima. What should be the angle of diffraction for your principal maxima, minima, and secondary maxima. So that's all for today. Thank you so much.